Realistic mirrors in games are cool. Cool because in many projects, they are simply absent. Even with ray tracing, it sometimes turns into a blurry mess. If I were you, I wouldn't stay here. Ghouls roam around here. But when a mirror actually looks like a mirror, oh, you notice it immediately. Well, you all know such technological hits as Mario 64, Half-Life 2, Duke Nukem 3D. Not like those mafias. What is this? Why is everything so blurry and laggy? This is how it should be. Have they forgotten how to do it? Now I'll tell you all about it. At the same time, you'll learn about different types of mirrors, how light works in games, or rather, how it doesn't work, how glare on weapons and first-person shooters is created, and of course, about ray tracing technology. So you're a developer who really wants to make cool reflections in your new game. Let's say, for example, because your project is a shaving simulator. In reality, it's simple. You take a lamp, shine it on your face, and place a mirror in front of it. Then the light reflected from your face hits the mirror. Photons bounce back into your eye, and voila, the picture is ready. What's the problem with doing the same thing in games? Just take an object with a mirror function, place it in front of the player, and that's it. Well, let's start with the fact that game graphics are, damn it, flat images. That is, every object is rendered from a certain perspective, and the computer simply doesn't know how it looks from another angle. Moreover, in games without ray tracing, the image isn't formed from reflected light, but from a bunch of hacks that imitate it. The mirror simply has nothing to reflect. Not like the age of GPUs with ray tracing, but that's a separate topic. We'll get to it later. The essence is that in older games, difficulties arose not only with mirrors, but also with lighting in general. Even a light spot reflected off a wall caused issues. In Metro Exodus, a rather modern example, by the way, creating high-quality lighting in this room required more than just placing 4 lamps. Instead, lighting specialists manually painted the room with light spots. Like, here's a lamp, here's a beam from the lamp, here's the reflected light from the floor, and so on. At the end, you also need to explain to the engine that if this lamp is turned off, certain lighting elements must also be disabled. It's incredibly tedious. Let's get back to reflections. It's clear that light is a complex thing, but nevertheless, here it is, a reflection in a 27-year-old game. Of course, it's a workaround. It's called planar reflection, meaning flat reflection. The essence of this workaround is so simple that, well, guess where the second Mario or Max Payne behind this mirror came from? Flat reflection, like there's a character behind it. Well, obviously. It's literally a duplicate of the level where the protagonist's model jumps, crouches, and does exactly what you do. You just can't get there. Since Nintendo 64, the process has been upgraded, and you no longer need to recreate the level from scratch to create such a mirror. But the essence remains the same. The computer simply renders the entire level from another perspective specifically for the reflection. The solution is so elegant, simple, and produces such a great result that no one will ever notice the trick if it's not pointed out. The funniest thing is that in terms of reflection quality, this implementation is still among the best. You've seen these reflections in Half-Life 2, Hitman 3, and The Last of Us Part 2, among many others. The approach is actively used, so why not include it in every game if it's so great? There's a reason. You've noticed in which locations this mirror is used. It's usually found in small spaces like bathrooms, where there are almost no NPCs, extra light sources, or tons of geometry. Plus, the reflective surface, as you see, is singular. If you want to place another mirror at a slightly different angle, you'll need to render 3 identical scenes and hope everything loads properly. In other words, the level will load the computer 3 times more than if there were no mirrors at all. Not the ideal option. Let's look further. What about reflections in building windows on the street? They're literally in every GTA, Watch Dogs, Spider-Man. Do they also render the entire city several times? Then why does the reflection here obviously come from another place? It looks that way because nothing here is rendered multiple times. A completely different principle is used. This type of reflection is called parallax-corrected cube mapping. There are many of these cube mappings, but the essence is the same. It's a cube with photos of the surrounding area pasted on its sides, a kind of 360-degree photo. This photo is taken and stretched around the object. That's the whole system. It's probably the most computer-friendly way to handle reflections. Nothing special needs to be rendered during the game. Reflection info doesn't take up much RAM and can be prepared in advance. This frees up the player's computer for other tasks. Hence, a number of problems arise. For full-fledged mirrors like in Mario 64, this style is entirely unsuitable. On a cube map, this 360-degree photo, your character won't be present. There are no cars, no dynamic objects at all. Moreover, cube maps are often used poorly. In Watch Dogs, you can clearly see the flaws of the technology. You approach a building, and the windows reflect an entirely different place. The world seems cool, beautiful, but then you look at this glass, and immersion goes straight to the trash. Chicago broke down. Bring a new one. And all because no one prepared a cube map specifically for this building. They took one from another point because there are too many buildings. You can't make maps for all of them, and there are more important things to do. This will do, they thought. Or look at a bug in the Resident Evil 4 remake. When inspecting a collectible item, the reflection shows some random park photo for the same reason. They just used a strange cube map. But for insignificant reflections, the method works perfectly. Adding an effect for a bottle or glass is an excellent solution. Even for racing games, the thing is suitable. In Forza Horizon 4, reflections on cars look pretty good even on Xbox One. Although here, in principle, the same cube mapping is used. How did that happen? It's because the developers at Playground Games are clever guys. They thought, but if a cube map is a square with 6 photos stretched on it, what happens if we change these photos in real time? And here's what happens. The car reflection map in Forza, or for example in GTA 5, updates in real time. That is, several cameras are placed around your car, rendering everything happening from different angles. Then the engine sends this information to the map, and voila, the reflections are ready. But this method has its drawbacks too. For example here, the headlights are at different distances from the viewer, but their reflections are absolutely identical because the map is the same. The resolution of the reflections leaves much to be desired. Well, Xbox One just can't handle 6 more renders of Forza. And the car itself isn't visible in the reflection because the camera shooting the cube map doesn't see it. But during a race, you'll never notice such problems. In general, cube mapping is also unsuitable for full-fledged high-quality mirrors. Before discussing the elephant in the room, let's look at another technology that does an excellent job of creating realistic reflections without any tracing. Seriously, the graphics in, for example, the aged but still beautiful Black Flag are the result of its work. For another example, you can look at the finals. This technique is called screen space reflections, or SSR, and is very often used in first-person shooters, although it's not uncommon in other genres either. With this thing, reflections are generated almost exactly as you see them in front of you. They don't put much load on the computer, and best of all, the system doesn't care about the complexity of the scene. Here are the same houses, the same bridges, identical. That is, the game doesn't care what to reflect. Be it a 4K explosion from Battlefield 5 or a landscape from Gulman. As the name suggests, screen space reflections use information directly from your monitor, processing the visible image. If you point the camera at a house with barrels, the game can easily take a kind of screenshot of your screen, tweak it a bit, and stick it in a puddle. That's it. The reflection is ready. It would be the best option on the planet if not for the drawbacks. As soon as the real non-reflected house disappears from the player's field of view, it also vanishes from the puddle. Disappears from the puddle. But dum tis. Or the problem from Alan Wake 2. Without using ray tracing, an NPC can simply block the background, and the reflection breaks. You've likely encountered this, and the main problem in our specific case is that your character isn't on the screen. This scheme won't help at all in showing what's behind the camera. Looks like there's no way out. Want cool reflections of large spaces? Turn on ray tracing. The thing that simulates light rays just like in real life. Actually, the technology is quite old. Here's Pixar's A Bug's Life from 1998. A movie like a movie, nothing special. Except that the lighting here is done exclusively with ray tracing. It's been a while, but the technology only made its full way into games recently in 2018 with the arrival of the RTX series graphics cards. They implemented special chips for calculating exclusively ray tracing. As a result, the process of building light was greatly accelerated. The technology fundamentally changes the approach to lighting in games. There was your regular night city, normal, nothing special, quite pleasant. And then it became this. Cool, everything reflects and glows, fire and everything. In short, the system replaces crooked hacks with a physically correct lighting model. Well, almost. The essence is this. The player's camera is taken, and rays are traced to light sources with all the bounces, reflections, and so on. That is, the path of the ray is calculated as in reality, but backward. Turns out now you don't need to create duplicate scenes to get cool mirrors. You don't. Let's start with the good. Ray tracing really solves a lot of problems. For example, Metro Exodus developers can now not engage in gymnastics. Just place those same 4 lamps and immediately get an awesome result. You can create locations faster, try more different design options, and the result will be even better than before. For players, ray tracing also offers cool features. Reflected light colors surfaces in different shades. For example, a blue curtain can change the shade of light throughout the room. Such a thing can be found in Far Cry 6, in Hogwarts, and many other places. Rooms are colored with very smooth transitions from light to shadow. Minecraft has notably improved under NVIDIA's CEO Huang. In short, it's very cool. Light fills the scene. But what about mirrors? As for them, well, how should I put it? Now you can reflect the player anywhere, in any mirror, cup, or car spoiler. Technically. In practice, when using tracing, a number of problems arise. First, it's a very heavy technology. If you try to calculate the rays without using graphics cards that support the technology, the player will have 6 frames, if not less. Second, not all existing cards, even those with ray tracing support, can handle full-fledged real-time reflections of everything. I'll tell you more. No modern card is capable of doing this at a normal frame rate, not even the 4090. And that's because the quality of tracing and ultimately reflections is influenced by 2 very important factors. The number of rays processed, for example, per second, and the number of bounces for each ray. The more of these, the better the picture. And the difference between ray tracings can be dramatic. Let's return to Metro Exodus. There's a separate old version of the game where light is implemented more simply, and there's one that runs exclusively on cards with tracing. In both versions, you can enable ray tracing. In the 2019 version, locations are sometimes very dark because the ray didn't bounce off walls. It went from the light source, hit something, and that was the end of its journey. In the enhanced edition, the picture became much better. Here, the ray learned to bounce off walls and floors. The result is obvious. Yet, in both cases, it's ray tracing. I understand it's not very clear what this has to do with mirrors, but wait a bit, I'll explain. We've figured out bounces. What about the number of rays? Here lies the key problem of ray tracing. No matter how hard the mentioned Huang tries, it's impossible to calculate every ray in the scene in fractions of a second. Many are calculated quickly, but we're talking hundreds or thousands of rays. But pixels on your screen, for example, on a 2K screen, are nearly 4 million. Each needs its own ray. Turns out if we take the result of the graphics card's work and apply no filters, the picture with this realistic tracing will look like this. I present to you noise. This grainy mess of dots from atomic heart footage. Calculated rays need technologies to suppress noise to turn them into something usable. For reflections on not very smooth surfaces, this isn't scary. No one will criticize a Kalashnikov for blurry highlights. But mirrors are a different matter. Reflections in mirrors must be sharp and smooth, but tracing can't yet reflect this pixel-perfect precision in real time. Noise suppression blurs the image, and as a result, it's decent, but quite blurry. Ultimately, either we sharply reflect some static object, the card needs time to calculate all bounces and rays, or we smear the result with a noise suppressor. Here's recent Alan Wake 2. The hero is standing right next to a mirror, but everything's blurry. Yes, ray tracing saves from some reflection artifacts, but the blur is incredible because of the noise suppressor. If you don't use it, it'll be sharper, of course, but everything will sink into gray pixels. And if you try to keep the image sharp and suppress noise like in Spider-Man 2, reflections will still distort, especially noticeable with foliage and other small objects. For the sake of a reflection in a puddle, forcing the card to calculate hundreds of rays and ending up with blur isn't optimal. That's why even in Metro Exodus and Cyberpunk with maximum tracing, screen space reflections still pop up occasionally. But they reflect not the entire picture, just what tracing can't handle, like foliage. Hence, when turning the camera, it disappears from the reflection. Moreover, many objects in the location are simply ignored in the reflection calculations because the player wouldn't see them in these reflections anyway. In Battlefield 5, the system even considers how large an object looks relative to the player. If a building is far away and takes up a dozen pixels on your screen, there's no need to calculate reflected light from it. But if you're up close to a lamp, it seems worth considering. Let me finally shatter your faith in ray tracing. Even in Cyberpunk with maximum ray tracing and path tracing of everything, turn on everything, and your reflection in the mirror will still be rendered through what? That's right, through flat reflection like in Max Payne. So, there's enough hassle even with ray tracing. The technology is heavy, not every hardware can handle it normally, and the result is still blurrier than a scene from Mario 64. Even in some cutting-edge Spider-Man, the hero's reflection drowns in artifacts on a high-resolution screen. You'll notice it without effort. Of course, there are ways to optimize tracing further. Minecraft uses light caching, meaning the light in a room is calculated once, and then you don't bother with it anymore. But it's unsuitable for mirrors because it's very slow. If you abruptly, well, how else, create a hole in a room, the light will slowly fill the space and just as slowly leave when the hole is patched. Developers seem to have given up on reflections because they haven't come up with a convenient and ready-made option. Yes, they haven't. But developers, of course, haven't completely given up. Tracing has solved reflection problems for specific scenarios. Silhouettes on cars, room lighting, distorted reflections in windows. For this, the technology is perfect. I myself can't wait to race in the updated Gran Turismo 7 with full ray tracing or, out of curiosity, jump into the Quake 2 remake. But for it, it'd be good to upgrade my GPU, you know. Such a thing at max settings in 4K, and even an RTX 4080 won't handle it. But with sharp, non-blurry mirrors, things are more complicated. To get an accurate image, you need so many rays and such a fast noise smoothing system that developers still have to ask themselves, do we really need a mirror in this location? If we need blurry reflections, say, for a car body in F1, tracing is perfect. Maximum reflection resolution isn't required in this case. But tracing allows you to accurately display the entire space around the car. When using cube maps, remember, the car itself simply doesn't reflect in its spoiler. But here, everything's fine. If you just need something to highlight a spinning gun in a Battle Pass window, you don't need to set up ray tracing there. Regular cube maps are enough. But for a mirror, the good old level duplicate or planar reflection is still the best choice. The most accurate result, the clearest, runs on almost any device. The only question is whether we can afford to render another room. And during development, these options remain to be combined with each other, even on the same surface. Light from lamps is calculated with ray tracing, light from the sky with cube mapping. Then everything is mixed, and it turns out nice. Many do this, from the old BF5 to the famous Cyberpunk and all sorts of Spider-Mans. If you see tracing in an already heavy game, there are likely similar tricks there. That's why, despite all modern technologies, clear mirrors in games are still rare, just as 30 years ago is now. However, With the new series of NVIDIA GPUs and the improvement of neural networks for noise smoothing in the image, the situation will likely change in the coming years. Write what you think about ray tracing technology and how much you personally miss cool reflections in games. I read the comments and will likely notice yours too. Don't forget to like, of course, and I'll say goodbye. See you in the next video.